All right, let's talk about vertical coherence. Now, let's connect elementary school to high school. That's exciting stuff, right? That's cool. Okay, so let's use a model to show how to multiply 15 times 13. I'm just going to put a model up on the board, okay? Notice as I draw. Why did I draw that model the way that I did? Take a few minutes in your brain and think, why would I draw that model the way that I did to multiply 15 times 13? Just take a minute to think. When you're ready, feel free to share. What do you think?
Well, we use this kind of area model with our younger grades, and it's nice because it breaks apart the ones and the tens places. And this way of multiplying, it's easier because you can do the math in your head pretty easily and then add.
So safe to say this makes multiplication a little easier, as well as more conceptual for kids.
Yes.
Perfect. So in the story of units for elementary school students, we use the area model. This is a form of the area model to teach students how to multiply multiple digits. So this is a 2 by 2, right? 2-digit by 2-digit multiplication problem. And so what it does, it really gets students to understand the distributive property, which they learn in elementary school as well, right? And so what they know is that they can either sum the partial products as layers to get their product, or they can sum all 4 partial products to get their product, okay? So in part A of your participant handout, this is the Algebra 1 Module 1, or as we know in North Carolina, it'd be Math 1, okay? Part A, go ahead and draw this model, please, and fill in the missing partial products. Take 30 seconds and take care of that. And just give me your eyes when you're ready to go. Sweet. All right, let's just kind of run through this real quick. Tell me what the 2 factors you're multiplying are and what the product would be, partial product.
Yep, 10 times 10 is 100.
Beautiful.
5 times 10 is 50. 5 times 3 is 15. 10 times 3 is 30.
Great. And so if I have 15 times 13, what we know is that this is the same as 10 plus 5 times 10 plus 3. So what you learned is that your product is
195.
Okay, and how did you get that again?
I went through and I summed 150 to get 150, and then 30 and 15 to get 45, and those 2 sums together get 195.
So 195 is our product.
Cool.
And so what we're going to get into here is that we see the concrete numbers that students use in their story of numbers in elementary school is going to lay a solid foundation for understanding the conceptual framework for why the standard algorithm of multiplication makes sense, right? This is going to lay some groundwork for why when we get that standard algorithm, it makes perfect sense. But what it also does is it lays a ton of groundwork for when students do some much more complicated work or complex work in the story of functions towards high school when they multiply polynomials, or in our case, binomials, okay? And so one quick thing I will note is that this is a rectangular array that students use in primary school. As they get to high school, we're going to call this a tabular method because quantities will become negative, and it is not accurate to refer to area as having negative quantities for lengths. So we're going to start using the tabular method. So in part B of your participant handout, could you use the tabular method, or what we know as the rectangular array, now tabular method, to multiply this polynomial, x plus 5 times x plus 3. Give it a shot. Pretty quick. Good application. Would you tell me about? I'm just going to kind of point. You tell me what you put. What did you put up here?
X. And then 5.
Oh, interesting. Okay, and then?
X. And then 3.
So let's talk about your partial products.
X squared.
How?
X times X.
Okay.
5X. 3X. 15.
Looks good. Let me ask you a question.
Mm-hmm.
You can do this in your brain. Just think for a minute. What do you notice about the partial products of your diagonals? So what do you notice about the partial products of your diagonals? Take 10 seconds to think about that for a minute. What you think?
They are like terms so can be combined.
Okay, give me an example of like terms that you see.
In this example, 5X and 3X.
Would give you
8X total.
Okay. What do you think you might put here?
Still the X squared.
And here?
Still the 15.
So when we multiply x plus 5 times x plus 3, what is the product? What do we get as our product?
What you just wrote in the diagonals.
Could you read that back for me?
Yep. So X squared plus 8X plus 15.
That should match, right?
Mm-hmm.
Okay. Let me ask you this. Take a second to think, again, on your own, of course. What do you notice about this vertical coherence that we're seeing from part A to part B? What's the coherence going on between the two? Take a second to think. What are you noticing?
It's the same exact process. It's just now in part B we have variables.
We're still using partial products
Yeah.
as a way to, we're adding our partial products
Correct.
to get a product.
Mm-hmm.
Cool. All right, what if we stepped it up just a little bit? We got one marker here. Okay, so in part C of your participant handout, we're actually going to talk about how we could reverse this process. How could we use our tabular method? How could we use our tabular method to factor a trinomial? So what I'm asking is, how could you use this method to factor this trinomial? Could you try to put together a model for how you might go backwards?
Yeah, I would look at part B and draw the blank boxes and then
A tabular method.
the tabular
Okay,
method.
gotcha.
And then include what you had in the red arrows and then the diagonals. And so you already have essentially the product and you're going backwards. So on the diagonal should be the x squared, the 2x, and then the minus 15.
So x squared.
Yeah, the 2x and then the minus 15. Yeah.
Okay. And so you called this your what? Use the
I
word.
said solution.
Okay. You also used the word
Product.
product. Beautiful. Okay.
Okay.
You're going backwards. Okay. Let me ask you this question: what partial products could we fill in right now? What partial products would we say, like, I know that?
Yeah, there's 2. So the x squared in the top left can be filled in.
Okay.
And then the minus 15 in the bottom right.
Can be filled in.
Yes.
Okay. That makes sense.
Yep.
What unknowns or blanks along your top and side could we automatically fill in? Do we know right away?
Yeah, well, x times x gives you x squared, and so the top left-hand side will be an x, and then on the down the side, the first number will be an x2, or the first value variable x.
Excellent. Okay. So we have some unknown values still. We have some partial products, and we have some blank values that we still need to figure out our binomials that would give us this trinomial if multiplied. Could you go ahead on your own, take about 30 seconds, could you come up with an explanation for how you could find these unknown values? Go for it. And then you are going to present this explanation. See our teacher's working hard right now. He's really going after it. Love it. Think you can do it?
I'm gonna try.
Gonna try. That's all we can ask for, right? That's all we can ask for is we put ourselves in an environment to try. All right, come on up and tell me what you think your unknown parts. I'll take a seat. See what I think. See what you think.
Okay, so with this minus 15 here, I need to find two numbers that multiply together to get minus 15, and then I need these two to ultimately add to 2x. And so the numbers that will do that are positive.
I'm gonna stop you. Could you give me evidence to prove that those two numbers need to add to 2x and that your two numbers also need to multiply to negative 15? Could you use a prior example to give me evidence?
Yeah, for both of them. So on the diagonal, they sum, and so 5x and 3x give you 8x, 50, 30 over here will give you 80 if you had written that out. And then similarly, over here, 5 times 3 gives you 15. Same numbers, 5, 3, 15.
Okay, cool. Good evidence. I like that.
Okay, so if that's the case, then positive 5 and negative 3 are the two numbers that need to go in here and here, and it doesn't matter which way they go.
What numbers would go in the...
Oh, sorry, this doesn't go here. Or were you asking for this first or this first?
Let's do the outside blanks first.
Great, so
What
it
would
still
go there?
doesn't matter. This can be a 5, here we go plus. This will be minus 3.
Perfect. Could you then give me your partial products?
Yeah, 5 times x gives you 5x. X times minus 3 gives you minus 3x.
That's correction. Isn't that fascinating?
Mm-hmm.
Wonderful. Thank you.